Now let's take a look at what would be possible when we start to examine diffusion from atomic level. Okay, we said diffusion is mass transfer, moment or motion of mass material through random motion of atoms or molecules or other species at a microscopic scale. Okay, it leads to motion. Now let's take a look at, okay, how do we understand this using one simple example, using so-called interstitial, because this one is the simplest one. Interstitial solid solution of B in A, which means which atom is smaller? Solid solution of B in A, which means B is smaller. Interstitial means B would be much smaller than the A. Okay, let's for simplicity. Well, quite often this course is about building a model, a physical or mathematical model. But when we build models, quite often we have to make assumptions or make simplifications. Let's for simplicity assume what types of lattice? Simple cubic. We don't often have this lattice, but that's the simplest one that we can construct. Okay, I draw it here. Simple cubic. Make sense? That's kind of a 2D projection of a 3D simple cubic lattice. And the A atoms are larger. The smaller red atoms are our so-called solute or impurity atoms, sitting where? At the so-called interstitial sites. Okay? And let's make assumptions. Let's define a term so-called gamma B. B for solute atom of impurity. Gamma B represent, read to yourself, average, means among all atoms, successful jump frequency. Average successful jump frequency. Frequency means it has a unit of 1/2. Okay, at the interstitial atom B. This is the first term that we define. Now let's take a look at plane 1. At this one plane, let's define another term called N1. Represent, read to yourself, area density. Specific density of what? Number density. Which means per unit area, how many number density, how many atoms? What atoms? B atoms. So N1 means the number density, area number density of solute atom at plane 1 that's cut around 1. Of course, we are doing projection, which just that one line. Make sense? Similarly, we can define another term at a different plane. N2 represent the, read to yourself, area number density of B atoms at which location? Plane 2. Okay. So now we define these two terms. Okay. And if we consider, we are considering diffusion within unit time. Within unit time, the flux of B atoms. JB, J for quite often for flux, B for the solute atom, the JB flux atom from plane 1 to plane 2. Okay, the B atom would be go wandering around, but from 1 to 2, we are considering only one direction, from 1 to 2, from here to here, 1 to 2 would be, I'll give it like this. Let's examine this equation and see if it makes sense. JB for flux of B atoms, and I put a arrow from left to right from 1 to 2. Make sense? Okay, it's 1/6 gamma B N1. What does N1 mean? The number area density of atoms in B. Okay, which means per unit area, how many B atoms are here? Okay, gamma B tells me what? Within unit time, how many successful jump for each of the solute B. So these two together tells us, okay, within unit time, how many of the B atoms are moving away. successfully moving away. But why do I put 1/6 here? Well, we are considering what? From 1 to 2, from here to here. In three-dimensional, if we are thinking of simple cubic, how many possibility? Up, down, front, back, left, right. Totally 6. And from 1 to 2 is only 1/6 of it. And we are assuming each of the atom is random, which means the probability of jumping from 1 to 2 is only 1/6 of the total successful jump for any of the atom. Make sense? So this term JB from left to right tells us the flux from 1 to 2. Similarly, from plane 2 to 1, you would write in a similar fashion, right? JB, the arrow goes from 2 to 1, JB, but now the arrow goes backward. Make sense? It's still 1/6 gamma B N2. Why do I use N2 here? Because I'm considering what I was starts at the 2 location, plane 2, right? The area density, which means per unit area, how many atoms. For each of the atom, it successfully jumps how many times, but for among all those times, only 1/6. If we think random, only 1/6 goes backward, right? So then, the net flux, now let's think, net flux from where to where? Along x direction, along x direction. The net flux from along x direction, which is from 1 to 2, kind of, the next flux would be the difference, right? Some of the atoms goes from 1 to 2. At the same time, some of the atoms would go from 2 to 1. So the net flux would be the difference between these two, right? Forward minus backward. And then we write it here. We put 1/6 in the front, gamma. We assume, assumption again, assume the successful jumping frequency is similar for solute atom at 1 versus at 2. And then N1 and N2 may be different. We leave them here, right? N1 and N2 may be different. Let's leave them here. Okay? So this flux would have the unit of meter minus 2 as second minus 2. Make sense? It means per unit area, per unit time, how many atoms are flowing net from kind of 1 to 2 location along my positive x-axis. Questions? Okay. So alpha, as we draw, what is alpha? We call it our simple cubic, which is just our lattice constant. Do you see that? Actually, from here to here is the same distance from one interstate to another interstate. So that's our lattice constant, which is the same as our so-called jumping distance, right? The lattice constant in this case would be the same as our successful jumping distance. Okay? And then let's think of a little bit. Quite often we say in diffusion we are concerned with what? C for concentration. We said downhill diffusion from high concentration to low concentration. Uphill diffusion from low concentration to high concentration. But typically, what unit does concentration have? Well, quite often, one would be number of atoms per unit volume, right? Quite often, that's how we define normally concentration. Volume concentration. How many number of atoms per unit volume? And the concentration at position 1 may be different from position 2. Okay, but how do we relate them together? I write something like this. C1, that means the concentration. Concentration here we mean how many numbers atoms per unit volume. C1, do you see that C1 is actually N1 divided by alpha? What does alpha mean? The lattice constant. If you draw a large kind of rectangular shaped curve along the number of atoms divided by the thickness of this slice. Do you see that? Will give you the volume concentration, which means the area number density divided by lattice constant give us the volume concentration. Let's look at this equation again. What unit does N1 have? Number per unit area, right? Meter square. And then divided by alpha. What unit does alpha have? Still meter, right? Now N divided by alpha. Now we have the unit of number per meter to the power of Q. Make sense? So this is how we relate so-called area density to volume concentration. Similarly, do you see that C2 would be N2 divided by alpha? Make sense? So now we can convert from number area density, which is how we define the number of atoms in plane 2, relates that to the local concentration, the volume concentration at plane 2. Okay, from these two, we rewrite, we are going to get N1 would equals to what? From here, N1 would equals to C1 times alpha, N2 would be C2 times alpha. Make sense? Okay. Now this is what we have. We said, okay, from previous slide, the flux, the net flux along my positive x direction from 1 to 2 location would be the difference of forward flux minus backward flux, right? That's what we got. The 1/6 represents the probability, gamma represents the frequency of successful jump, N1 and N2 are the so-called area number density. And then from previous, we relate N to what? Area density to volume concentration, right? That's what we got at the end of the slide. Now we rewrite. What did we do? We replace N1 with alpha times C1, N2 with alpha times C2, and then what did we do? Alpha is the same for the same lattice, right? Now we put alpha in the front. Now we have the total flux along my positive x direction would be 1/6 gamma alpha. We have a difference. Make sense? Okay. Now let's think of reality. We are dealing with jumping of atoms at a microscopic scale, small distance. So as you can imagine, this alpha is a big number or small number, meter or nanometer? Nanometer, small, right? Pretty small. This concentration difference across two neighboring lattice sites would be also a small number. Make sense? So as a result, do you see that this ratio, the difference in concentration divided by the distance, physical distance, is a small number over a small number, right? What does C1 and C2 mean? Number area density at location 2 versus location 1. Remember we said 1 and 2 are right next to each other and they are separated by the distance of alpha. So these two, both the numerator and the denominator are very small number. Do you see a mathematically we can write it as the partial differential? Make sense? Because it's small number over small number, it just means the partial differential, partial derivative. Okay? And then now let's look at our flux equation again. This is what we have. J is 1/6 gamma frequency, alpha jumping distance, C1 minus C2. Do you see this? It's the same equation we borrowed down. Now we do the mathematical manipulation. How did we do? Do you see this? What did we do? We have alpha, now we have alpha square. Because we have alpha square, we have to put one alpha at the denominator, Well, this guy C1 minus C2, because I have C1 minus C2, I rewrite as C2 minus C1. I need a minus sign here. Make sense? So now borrow from my middle equation. Do you see this fraction can give me the partial derivative? Make sense? I still have minus sign here. My gamma alpha squared term got kept, but my fraction term got replaced by the partial differential. Make sense? Okay. Then this is what we have. J, the flux of what? The solute impurity interstitial atoms of B along my chosen positive x direction would be 1 over minus 1 over c gamma alpha square, a partial differential of concentration. Okay? And then if we define the so-called diffusion coefficient, what do we define? This term, 1 over 6 gamma alpha square. Again, 1 over 6 means, okay, the jumping in this simple cubic, only 1 in 6 direction possibility goes towards the direction that I want, right? And this gamma is a successful jumping frequency. It can jump up, jump down, jump front, jump back, jump left, jump right. Okay, among them 1 in 6 counts. Alpha is my successful jumping distance from one interstitial side to the neighboring interstitial side. Okay, do you see this is pretty much a fixed number if we are given a fixed temperature, if we are given a fixed lattice, right? A fixed lattice, the jumping distance pretty much fixed. At a fixed temperature, the successful jumping frequency pretty much fixed. So this is what we call diffusion coefficient. What unit does diffusion coefficient D has? What unit does alpha has? Lattice parameter or jumping distance has meter, right? Alpha square, meter square. What unit does gamma has? Remember, as frequency. It has a unit of hertz or 1 over second. So do you see this D would have that strange unit of meter square divided by second? Make sense? So diffusion coefficient has such an interesting unit, meter square per second. And then this is what we have. J means flux is minus, we keep it minus, this sin 1 over 6 gamma alpha square we define as our diffusion coefficient, which is dB, we write it down here, and then the last partial differential term we write it down here. Okay? So this equation, people call it, repeat to yourself, Fick's first law. Fick's first law. It relates what? It relates J for flux. Per unit area, per unit time, what's the number of atoms, molecules, electrons flow along the direction that you are interested. It's determined by a constant, which we call diffusion coefficient, and also a differential term. What is that differential term? So-called concentration with respect to location. That's for 1D. In 3D, we would call it concentration gradient. How fast does concentration change with location? Make sense? If we are only dealing with one direction, that's x. If we are dealing with three-dimensional, that would be so-called concentration gradient. This is our Fick's first law. Very, very important. Questions? And what does this tell us? It tells us, okay, if we have a concentration along x is decreasing, which means this term would be negative, our flux would be positive, right? If this partial differential term is negative, which means along the x is decreasing. Actually, the j would be positive, which means it will go along the x direction. On the other hand, if we assume dB is positive, there may be situation that dB is negative. That's what we call the uphill diffusion. Believe it or not, that's uphill diffusion when it happens. Okay.